to the
Picture a
German
September
fighter
morning
groups
in 1940.
and even see the distinctive
The sky over
twin-boomed
England is quiet, almost deceptively calm. In the dim light, a
Target and out
Heinkel
again.
He-111 slices
300
through
miles
the
and
clouds,
more each way.
carrying a deadly cargo.
That's
2
the
tons
key
of
to a
bombs
ramrod.
aimed at the teeming streets of London.
Tank is
One can
on,
almost feel
and
the
finally
tension.
the gas.
Would this plane reach its target, unleashing destruction below? Perhaps it might have, if not for the ingenuity of Britain's home
The
defense.
film The Thunderbolts,
Long
Ramrods
before
to
the
Emden,
roar of engines signaled danger, a
documented.
network of
A
radar
crucial
stations
battle
was
of
scanning the
strategy and
skies.
courage was being done,
Every blip of incoming
capturing the
enemy
meticulous
aircraft was
planning, the
transmitted
tense
to a
pilot
central
briefings,
operations room, where officers rapidly verified and mapped each threat on a sprawling chart of Britain. This was the nerve center from which all RAF commands during the Battle of Britain were issued. Every second counted. Each tick of the clock stole precious moments from the pilots, moments they needed to climb to interception altitude and meet the enemy head-on. Thanks to this revolutionary air defense system, British fighters could be in the air within 10 minutes of the first radar warning. Yet speed alone was not enough. The aircraft themselves had to be exceptional, capable of scaling
we
the
get a
skies
rare glimpse into
as
the
swiftly
operations
as
of the
danger
56th
approached.
and 4th.
Enter the Spitfire. This legendary fighter could climb at a staggering 760 meters per minute, reaching its target's altitude in just 4 to 5 minutes. Agile, responsive, lethal. This was no mere plane. It was a soaring embodiment of defense and daring. But how did it achieve such prowess? The answer lies in brilliant engineering. The Spitfire's design demanded power, precision, and firepower in equal measure. Some of World War II's greatest minds devoted themselves to crafting this masterpiece, and in doing so, changed the course of the war. To truly grasp its genius, one must consider the context. By 1936, the RAF was still flying biplanes like the Gloucester Gauntlet and Hawker Fury, their stacked wings producing lift, but also massive drag. The world had yet to witness what could be achieved with all-metal monoplane fighters, powered by new engines and revolutionary aluminum alloys. Dear friends, if this video has reached you, it's not by chance. Right now, click the subscribe button and the notification bell. Write a number from 1 to 5 in the comments. I will personally respond to the first 50 comments and make sure to watch the video until the end. R.J. Mitchell, the Spitfire's chief designer, seized this opportunity. Freed from the constraints of old designs, he aimed to build a plane that could outrun and outmaneuver any foe. Central to this goal was turn performance, the art of the dogfight, measured by the minimum turn radius a plane could achieve. How does an aircraft turn? It rolls into the direction of the turn, creating a bank angle. This divides the lift into 2 forces. One vertical, keeping the plane aloft, and one horizontal, driving the turn. Steepen the bank, and the plane can pivot more sharply, but at the cost of vertical lift. Too much tilt, and the aircraft risks losing altitude. Pilots countered this by adjusting the elevators to maintain lift, but that, in turn, increased drag, demanding more engine power to preserve speed. The Spitfire's ultimate edge came from optimizing sustained turn performance, the tightest, fastest turn achievable without losing altitude or velocity. This depended on 3 things: the aircraft's weight, engine power, and wing design. Mitchell, drawing on his experience with the Schneider Trophy-winning Supermarine S5 of 1928, labored to perfect the wing. Early concepts, like a straight-tapered design from 1934, would have been simpler to build, but performance demanded more. The elliptical wing, elegant and iconic, provided an ideal lift distribution, reducing the energy-sapping vortices that form at wingtips, though Mitchell himself famously quipped, "I don't give a bugger whether it's elliptical or not, so long as it covers the guns." The elliptical wing's true brilliance, however, lay elsewhere. Its curved shape preserved chord length near the fuselage, providing ample internal space for landing gear, guns, hydraulics, radiators, and structural supports. This allowed the wing spar, the backbone of the wing, to remain lightweight yet strong, giving the Spitfire the audacity to execute daring maneuvers without fear of structural failure. Engineers faced a delicate balancing act: increased strength and weight rises, reducing climb and turn performance while increasing fuel consumption. Even the Spitfire's wing was not perfectly elliptical. Its trailing edge curves inward, faster than the leading edge, a subtle but critical adjustment. This ensured that the wing spar aligned with the quarter cord, the aerodynamic center where lift effectively acts. Without this, lift would twist the wing, demanding extra reinforcements and weight. Every line, every curve, every component was meticulously designed to maximize performance while minimizing burden. In the Spitfire, art and engineering merged to produce an aircraft that was not just a plane, but a weapon, a guardian, and a symbol of defiance. Imagine standing on the wing of a Spitfire. Not literally, of course, but picture the engineering marvel stretching out before you. From root to tip, the bending forces the wing must endure diminish as you move outward, allowing the spar, the backbone of the wing, to taper in strength and weight along its span. But in the 1940s, shaping such a complex structure was no simple task. Today, we take for granted the ability to sculpt single components into intricate forms with CNC milling machines tools that engineers during World War II could only dream of. To cleverly manage this, the Spitfire's wing spar was crafted from nested square extrusions. The upper and lower spar booms weren't monolithic pieces. They were composed of 5 concentric aluminum square sections, meticulously cut and fitted inside one another like a perfect set of Russian dolls. This was more than construction, it was artistry. The result? A wing that granted the Spitfire breathtaking agility in the skies, a maneuverability that would define its legend. Now, let's compare this to the Messerschmitt Bf-109, the Spitfire's rival during the Battle of Britain. Noticeably, the Spitfire's wingspan was larger. This wasn't mere aesthetics, it directly impacted wing loading, a crucial performance metric calculated as the aircraft's weight divided by its wing area. Lower wing loading meant tighter turns. The Bf-109, with its smaller wings, had a higher wing loading, resulting in broader, less nimble turns. Imagine dogfighting in the clouds. The Spitfire could slice through arcs that would leave a 109 struggling to keep up. The wings weren't just about aerodynamics, they were weapons platforms. Early Spitfires could house 8 Browning machine guns inside the wings. Later models evolved, carrying 2 20mm cannons alongside 4 7.7-meter Brownings, all safely mounted outside the propeller arc. Messerschmitt engineers, on the other hand, faced far more intricate challenges. To fire through the propeller, 2 machine guns perched above the engine had to be timed perfectly with an interrupter gear. A cannon might even fire through a hollow tube threaded inside the inverted V12 engine and out through the propeller hub, a solution as brilliant as it was complex. Later attempts to mount guns in the 109's wings were hindered by ammunition storage, requiring unreliable belt-fed chutes from the fuselage or awkward gun pods under the wing that impaired handling. At its heart, the Spitfire was designed as an interceptor. Speed and climb were paramount. The secret lay in power-to-weight ratio, a delicate balance that demanded Britain's brightest minds. The legendary Merlin engine, evolving constantly over the war, aimed to extract ever more horsepower from its 27-liter displacement. Displacement, the volume swept by the pistons, directly influenced power. More displacement means more air and fuel combusted, more heat, more pressure, and ultimately more thrust. But adding fuel isn't as simple as it sounds. There's an optimal air-fuel mixture, roughly 12 parts air to 1 part fuel. Altitude added complexity. At 500 meters, air pressure is halved, cutting oxygen supply and threatening power output. To counter this, the Merlin incorporated a supercharger. Air entered beneath the fuselage, passed through a float carburetor, essentially a tiny tank with a float acting like a toilet cistern, to maintain the perfect fuel level, and then into the supercharger, where it was compressed before hitting the pistons. But this float carburetor had a vulnerability. In a negative G maneuver, the float would drop, flooding the engine with fuel and causing it to cut out. German pilots flying the WWII had direct fuel injection, a sophisticated system with 12 plungers and cams to time the fuel precisely, letting them dive under negative G without losing power. A maneuver that forced Spitfire pilots to roll first to maintain positive G, buying the WWII precious seconds to escape. The supercharger itself boosted the Merlin's output, helping a 27-liter engine rival the 34-liter DB601, powering the BF109. Early Merlin engines, however, featured a single-stage, single-speed supercharger tied directly to the crankshaft. Peak power arrived around 10,000 feet and fell off sharply above or below, necessitating a throttle on the air intake to protect the engine as the aircraft climbed. By contrast, the BF109 supercharger was a marvel of flexibility. Positioned at a 90-degree angle, it used a fluid coupling to transmit engine power. Oil inside the coupling rotated, driving the turbine, while a pump adjusted oil volume with altitude, allowing the supercharger to vary its speed. The result: superior low-altitude power, a decisive advantage for the BF109E during the Battle of Britain. While the Spitfire could outturn the WWII, the German fighter could exploit its better power-to-weight ratio to maintain climbing turns, outmaneuvering Spitfires trying to stay on its tail. British engineers were acutely aware of the Merlin engine's limitations even before the Battle of Britain erupted, and by mid-1940, work had begun on a revolutionary solution: a two-stage, two-speed supercharger. Imagine the challenge. They needed a mechanism that could operate at 2 different speeds, yet also compress the air more effectively for high-altitude performance. Enter the second impeller, a brilliant addition that boosted compression and allowed the Spitfire to chase enemies into thinner air. But engineering brilliance often comes with trade-offs. Higher compression meant hotter air entering the engine, which could sap efficiency and risk overheating. The answer? An intercooler, designed to cool the supercharged air before it reached the pistons. This clever device removed roughly a third of the heat generated by the supercharger, striking a delicate balance between cooling efficiency and aerodynamic drag. You might wonder, why not just cool the air even more? The problem lies in physics. A larger intercooler would require a bigger radiator, and a bigger radiator increases drag, which in turn would cancel out the engine's power gains. It was this precise juggling act between cooling, weight, and aerodynamic efficiency that allowed the Spitfire to extract extraordinary performance from its comparatively small Merlin engine. German engineers took note. In meetings among Germany's aviation development chiefs, Messerschmitt pointed out how the Spitfire's radiators were half the size of their own. But the Germans faced a critical limitation. Their engines could not handle the higher coolant pressures required to shrink radiator size without risking leaks. The British, on the other hand, had decades of experience with high-pressure, high-temperature cooling systems, honed in the high-speed racing circuits of events like the Schneider Trophy domain, barred to Germans under the Treaty of Versailles. By increasing coolant pressure, British engineers could raise operating temperatures without boiling, dramatically improving the radiator's efficiency. A smaller radiator meant less drag, even if it had to be reinforced and made slightly heavier. The result was a formidable machine. The Spitfire, paired against the Bf-109, faced an enemy of equal prowess in the skies. Yet the outcome of many dogfights hinged less on the aircraft themselves and more on the human skill of the pilots, combined with the strategic advantages of defending one's own soil. The Battle of Britain was decided in these narrow margins, and every innovation, from the elliptical wings to the supercharged Merlin engine, helped tilt the scales in Britain's favor. But even the finest fighters could not have prevailed without the intricate network of ground support. Radar stations, data processing, detailed mapping, strict chains of command, rigorous pilot training, and even the careful management of fuel octane all converged to create an environment where the RAF could respond, day after day, to the Luftwaffe's onslaught. For those who want to explore this extraordinary history in even more depth, every element, the custom-built operations room at Bentley Priory, the animated reconstructions, the technical breakdowns of aircraft, has been brought to life in our Nebula original series, The Battle of Britain. With 4 episodes already available and more on the way, the series dives deeply into both the human and engineering stories of this pivotal moment in history. Fans of World War II history may also enjoy our 7-part series on the logistics of D-Day, or Wendover Productions' recent feature on Wake Island, a tiny, remote Pacific outpost with an outsized story in aviation and the Second World War. And for those who wish to support independent creators, subscribing to Nebula via the Curiosity Stream and Nebula Bundle for just $14.79 a year unlocks ad-free viewing and exclusive documentaries, an entire year of meticulously researched history and science content, all at your fingertips.